This video, we discuss linearly independent and linearly dependent sets of functions. We'll provide some context, including why this is important. We'll define linearly independent sets of functions and linearly dependent sets of functions. And then we'll talk about the Wronskian, which is a test that will allow us to test a set of functions to determine if that set of functions is linearly independent on an interval or linearly dependent on an interval. So first, we'll provide the definition. And the definition is this. We say that a set of functions f sub 1 through f sub n is called linearly dependent on I if there exist constants c sub 1 through c sub n. Not all 0, that is really important, such that c1 times f1 plus c2 times f2 plus c sub 3 times f sub 3 all the way through c sub n times f sub n is equal to 0 on I. So if you can take this set of functions, multiply them by appropriate constants in such a way that when you add them together, you get 0, if that's possible, where those constants are not all 0, then we say that that set of functions is linearly dependent. Otherwise, we say that that set of functions is linearly independent on that interval. You might be saying to yourself, okay, why should I care about this? Why is this important? And this is important because of what we talked about in the last video. Remember, in the last video, we said that when we're talking about solutions to homogeneous, linear, ordinary differential equations, and those are differential equations that look like this, y and y's derivatives are all raised to the first power, or they don't appear in the equation at all. The coefficient functions, those are the functions in front of y and y's derivatives. They depend only on that independent variable. And there's no composite function involving y and y's derivatives anywhere here. So it's linear, and the coefficients depend only on x or t or whatever the independent variable is. We said in the last video that the general solution to this nth order differential equation comes from taking a set of functions, y sub 1 through y sub n, and those functions have to be linearly independent, which is what we're about to talk about. If you have a linearly independent set of functions that satisfy this differential equation, so y sub 1 through y sub n are all solutions to this differential equation, and they're linearly independent from each other, then all you have to do to find the general solution is multiply them by constants and add them together, and that's the general solution. So when we're solving homogeneous linear ODEs, what we really want is this linearly independent set of functions. And it's not just a set of functions, it's a linearly independent set of solutions to this differential equation. So it's really important that we're able to tell the difference between linearly independent sets of functions and linearly dependent sets of functions. So that's why this is important. And again, just for emphasis, if this is an nth order equation, there are n solutions here. So if this is a fifth order equation, I'd have 5 linearly independent solutions, y sub 1, y sub 2, y sub 3, y sub 4, and y sub 5. And if this was a third order equation, I'd have 3 solutions, y sub 1, y sub 2, and y sub 3, all linearly independent from each other. If we multiply those by constants and add them together, that gives us the general solution. Okay, now if you're saying to yourself, but what does this really mean? It looks like a bunch of algebra, and it may not be 100% clear what this is doing for us and how this relates to this. Like, we could probably verify this fact for a set of functions without really understanding what's going on. So I'm going to look at a special case of this to help us understand what's going on, to help us understand what it means for a set of functions to be linearly independent. And to help us understand, let's look at just a set of 2 functions. So let's say that we've got 2 functions, f sub 1 and f sub 2, and this is a linearly dependent set. On some interval I. Well, what that means is that this is satisfied for some c sub 1, c sub 2, not all equal to 0 on that interval. So this is true for some constants C1 and C2, and they can't both be 0. And this is true on the interval I. Okay, so let's think about what this means. Well, first of all, let's just assume that if they're not all 0, let's say one of them is 0. Let's say C1 is 0. Well, if C1 is 0, then this term is gone, and then we just have C2 times F equals 0. Oops, that should be an F sub 2. That's our second function there. Well, if F2 is not the 0 function, and we're assuming that F sub 1 and F sub 2 are not the 0 function, neither of them are the 0 function, then the only way that this constant times F2 is equal to 0 is if C2 is equal to 0. So we said if C1 equals 0, then in order to get a 0 over here, C2 must be 0. But that can't happen because these constants are not all allowed to be 0 if we've got a linearly dependent set of functions. And the same would be true if I assumed C2 is 0. Well, then if C2 is 0, we'd have to have C1 equal 0 in order for this times a non-zero function plus this times a non-zero function to be 0. Okay, so what that means is that C1 and C2 must both be non-zero. The only way for this to work is for C1 and C2 to be non-zero. Well, in that case, I can take this equation and I can solve for F sub 1. Let's subtract C2 times F2 from both sides and then divide both sides by C sub 1. And we get this. Or in other words, F1 is a constant times F sub 2. So that means that if we have a linearly dependent set of two functions, then F sub 1 and F sub 2 must be constant multiples of each other. This is linearly dependent, not independent, sorry. And I hope that this helps you understand a little bit of what we mean when we say that a set of functions is linearly dependent. When I go up here, I want this y sub 1 through y sub n to each contribute something unique to this solution to the differential equation. Now, if I've just got a second order equation, I would have two solutions, y1 and y2. Now, if I have two solutions, y1 and y2, and they're linearly independent from each other, that means they can't be constant multiples of each other. Because if they were constant multiples of each other, they'd be linearly dependent. And if you're saying to yourself, well, why is that a problem? Well, let's think about it. Let's say that we had, for a particular differential equation, we had a solution y1 equals x squared. And then you came along and I said, I'm looking for a second solution to the differential equation. And you said, oh, you know what will work? 5 times x squared. And I would say, well, yeah, remember what we talked about before? If y1 equals x squared is a solution, any constant times x squared will also be a solution, including 5x squared. So I kind of already knew that 5x squared would be a solution because I knew that x squared would be a solution. So this is not telling me anything new. This function has already taken care of all of the multiples of x squared. So this set of functions, x squared and 5x squared, is linearly dependent on the entire real line. They're linearly independent only when x equals 0, but we're talking about intervals of values. So that x equals 0 value is not our primary concern here. This is linearly dependent. So if I were looking for a solution to a second order equation, and you told me that this was, and I knew that this was a solution, I would have to keep looking for a second linearly independent solution if you gave me this one. This solution is not contributing anything new. there's another function out there, if it's a second order equation, there's another function out there that also satisfies that equation that is not a constant times this one. In that case, that function x squared and that other function that's linearly independent from x squared that satisfies the equation, that would form the linearly independent set of solutions, and we could multiply them by constants and add them together, and they would satisfy the differential equation. So 5x squared is not giving me anything that x squared is giving me, so this is a linearly dependent set. Now you could also look at this in terms of this equation right here. You could say to yourself, okay, is it possible for me to take one of these functions, multiply it by a constant, and take the other function and multiply it by a constant and add them together and get 0? Or in other words, is it possible to choose C1 and C2, not both 0, such that C1 times x squared plus C2 times 5x squared is equal to 0? Is it possible? Can you choose C1 and C2? Well, I know if the C1 and C2 are both 0, we clearly get 0, but that's not what we're saying here. We're saying that the constants have to be non-zero. There are lots of possible combinations that you could use, but if I chose C1 or C sub 2 to be 1, and at the same time I said that C sub 1 is, say, -5, -5 times x squared plus 1 times 5x squared would give me a 0. So this would imply that this set, x squared and 5x squared, the set of functions, is a linearly dependent set on the real line. Now, most of the time we don't spend our time guessing like this. We don't try to find C1 and C2. But we remember this idea that if you've got a linearly independent or a linearly dependent set of two functions, the two functions are constant multiples of each other. Now, the same is true with linearly independent sets of 3 functions. Let me give you an example. Except it's not as strict. It's not constant multiples in this case. So let's say you've got 3 functions, 2x and x cubed, or x squared and 5x squared minus 4x. So you've got 3 functions there. The question is this a linearly independent set on, let's say, the entire real line? That's what we want to know. Well, we can use the definition to figure that out. But again, I want you to think of this in terms of functions being redundant. The question is there any function on this list that I can get from the other 2 functions? Now, these are linearly independent because if I take this one and multiply it by a constant, there's no way I'm getting 5, or no way I'm getting x squared out of that. And if I take this one and I multiply it by a constant, there's no way I'm getting 2x. Now, if you're saying to yourself, well, you could multiply that by a 1/2 x to get that one, you're right, we could, but 1/2 x is not a constant. So these 2 are linearly independent from each other, and these 2 are linearly independent from each other, and these 2 are linearly independent from each other, because no subset of 2 of these functions includes 2 functions that are just constant multiples of each other. But now we're looking at a set of 3 functions and we're asking, are there any functions on this list that are redundant? Or in other words, is there any function on this list that I can get by taking a linear combination of 2 other functions? A linear combination is just a function times a constant plus the other function times a constant. Can you get this function by multiplying these 2 guys by constants and adding them together? I think you can. So this is actually a linearly dependent set. Now let's prove it just using the definition. So I need to choose constants C1, C2, and C3. such that I get a 0 here. The question is, can it be done? Well, I think it can, because if I've got a 5x squared over here, if I make this c sub 3 a 1, in order to get rid of that 5x squared from here, I could make that c sub 2 a negative 5. So that I'd have a negative 5x squared plus 5x squared is 0x squared, and the x squareds would be gone. Now the question becomes, well, what about this 2x? Well, I can use the 2x to get rid of that negative 4x there. If the coefficient of this were a 4, if this was a 4x minus a 4x, I'd have 0 there. So I'll just choose C1 to equal 2. So 2 times a 2x is giving me a 4x. So I've got 4x minus 5x squared plus 5x squared minus 4x. And I think we can all see that everything cancels. Everything just disappears. So this 4x reduces with this negative 4x. This 5x squared reduces with that negative 5x squared. So one of these functions is redundant. If you can choose C1, C2, and C3, not all 0, so that you actually get a 0 out of here, that means one of the functions is redundant. So that set that we just looked at is a linearly dependent set by definition. And with the constants that make that equation true here are C1, C2, and C3 equal to 2, negative 5, and 1 respectively. But again, it's this idea of sets of functions being redundant that is really like the main idea here. If I'm saying that this is a linearly dependent set, what I'm saying is I can get this function by taking combinations of these functions. So that's just another way of saying this. We can rearrange this equation. So you have just this function on one side, and then you'd say, how can I get this function from these two functions? Well, if I multiply this first one by 5, and I multiply this one by negative 2, and then I add them together, I'd have 5x squared minus 4x, and that's going to give me this one. So this function is not giving me any new information that these two functions aren't already giving me. So this function is the one that we probably want to leave out if we're trying to form a linearly independent set of functions. Now, I had a very bright student in my class ask the question, how do you know to leave out this one? He said, how do you know that that's the one that's linearly dependent that you can get from the other two? Actually, the truth is these two form a linearly independent set because this one is not a multiple of this one. These two form a linearly independent set because this one is not a multiple of this one. And then these two form a linearly independent set because this one is not a multiple of this one. So actually any two of these three functions form a linearly independent set. But I think it's most obvious that this one is just a combination of these two. So I'd probably get rid of this guy and then just focus on these guys and keep those in my fundamental set of solutions. Now, if you have a third order differential equation and you're looking for a set of 3 linearly independent functions that are all defined on the same interval I, and you've got 2 functions, you will probably also know the third based on the algorithms that I'm going to teach you in this class for finding the fundamental set of solutions to that third order differential equation. So most of the time this doesn't happen. You don't say this is a solution and this is a solution. Is there another solution out there? And somebody says, yes, this one. And you say, no, yes, that I know that that's a solution because these two are solutions. this is a linearly dependent set, and this is not offering any new information. Now, if you're a student and you're thinking, but if that happened, how would I know how to find the third solution? Don't worry about that. We actually have a method called reduction of order that might help in that case. But for the most part, we have methods that will allow us to find all three solutions of that third order equation. So really what we're getting at here is the concept of linear dependence and linear independence. And a linearly dependent set of functions includes at least one function that is redundant, that it can be found by just taking a combination of the other two. Now, we don't usually like to use this formal definition of linear independence every time. Like guessing constants C sub 1 and through C sub n that are not all 0 that make this true is kind of tedious. So we like to have an algorithm that we can apply every time to determine whether a set of functions is linearly independent or linearly dependent on an interval. And actually using the Wronskian will allow us to do that. So let me define the Wronskian for you and then show you how to evaluate it and then talk about what it means. Excuse me. So the Wronskian of the set of functions f sub 1 through f sub n is the determinant of that set of functions, or is a determinant involving that set of functions. We can write it this way. In the top row, you write f sub 1, f sub 2, f sub 3, all the way through f sub n. And in the next row, you list their first derivatives. So you take the derivative of each function, and then in the next row, you do that again. And then you keep going until you have a square matrix. So we've got n columns here, 1, 2, 3, all the way through n, and we want n rows. So that means we're going to go all the way down to the n minus 1th derivative. So if there are 5 functions here, we're going to take the 4th derivative. And that goes over here. Now, for the most part, you're just going to do 3 by 3 determinants, not 4 by 4 determinants. 2 by 2 and 3 by 3 are plenty. So the Wronskian of a set of functions is the determinant of this n by n matrix. And this is going to allow us to determine whether that set of functions is linearly dependent on an interval or linearly independent on an interval. So here's just a fact. If the Wronskian of a set of functions is equal to 0 on an interval I, then that set is linearly dependent on I. It's a linearly dependent set. If the Wronskian of that set of functions is non-zero for any particular value of the independent variable on the interval I, then the set of functions f sub 1 through f sub n is linearly independent on that interval I. So you're going to evaluate this determinant. First, you're going to set it up, then you'll evaluate it. And if it's 0, you know these functions are linearly dependent. If the Wronskian is non-zero, you know that the set of functions is linearly independent. Now, often you have a Wronskian that is equal to 0 sometimes. So you might have a function of x or a function of t over here. And you might say, oh, but when x equals 3, this is equal to 0. Well, you'd say, well, at exactly x equals 3, this set of functions is linearly dependent. But when we're talking about that set of functions being linearly independent or dependent on an interval I, we need this to be 0 for all x values on the interval. So when you evaluate this, if you actually get a 0, then the set is linearly dependent. And if you don't get a 0, it's some other function, then the set is linearly independent on that interval. Okay, so let's actually practice with this. Let's use the Wronskian. To determine whether the set of functions is linearly dependent or linearly independent. And let's say that the functions that we're interested in this time are these. So I've just written those down while I paused the video. I looked this up in a book and I found a good problem. Okay, so these are our two functions. F of t equals t squared, and f of t equals t squared times e to the negative t. Now I think that we both know, or all of us know, everyone who's watching this video knows that this function is not a constant times this function. To get from here to here, I had to multiply this guy by an e to the negative t. So these are not linearly dependent because they're not multiples of each other and it's just a set of two functions. If I want to prove that using the Wronskian though, this is what we do. We set up this 2 by 2 determinant. In the first row, you've got t squared and t squared e to the negative t. So that's f sub 1 and that's f sub 2. And then the second row, you take the derivative. The derivative of t squared is 2t, and the derivative here requires the product rule. The product rule says, if this is my first function and this is my second function, we'll take the derivative of the first and multiply by the second, and then add the derivative of the second. Derivative of e to some power is e to that power times the derivative of the inside by the chain rule. That's the derivative of the second, and we multiply it by the first. And then you just evaluate this 2 by 2 determinant. Now you may have forgotten how to evaluate a 2 by 2 determinant. It's actually really easy, very, very easy. So here's the formula. Sorry, I'm having trouble with my little papers here. So if you have a 2 by 2 matrix like this with entries A, B, C, and D, to find the determinant, you just multiply across this diagonal from the first row, first column, down to that last row, last column. And then you multiply across this diagonal and you subtract. That's it. Very, very easy. And then we'll talk about how to evaluate a 3 by 3 determinant when we look at one of those in a moment. So we're here and we're trying to evaluate this 2 by 2 determinant. It might be helpful with this guy if we simplify it first. Let's rewrite this way. We've got t squared and 2t in this column, and t squared and e to the negative t in that first row, second column. And then down here you have an e to the negative t and an e to the negative t. So I would factor that out. These two guys also have a t in common. Yeah, I'll factor that out as well. So we'll factor out t times e to the negative t. And then we ask ourselves, this times what will give us this first term? Well, the only thing that's missing is a 2. So we'll just put that there. And then we ask ourselves, this times what gives me my second term? Well, I'm missing a negative, and I already have this, and I have one of these t's, so I need another t. So I've got that there. So we're evaluating this 2 by 2 now. And we multiply across this diagonal and subtract. This times this gives me t cubed e to the negative t times 2 minus t. And then this times this gives me plus 2t cubed e to the negative t. And I guess we need to distribute now. Let's go that way. So we'll have 2t cubed e to the negative t minus t to the fourth e to the negative t plus t cubed e to the negative t. We end up with 4t cubed e to the negative t, combining this guy and this guy, and you're subtracting t to the fourth e to the negative t. So from here, you can factor out a t cubed e to the negative t. That times 4 gives me my first term, and that times a negative t gives me my second term. And that's clearly non-zero when we're talking about an interval of t values, all real numbers. Now you can also see that this is equal to 0 when t equals 0 and when t equals 4. That's completely okay. When we're talking about the entire real line, this is not equal to 0. That means that the set of functions t squared and t squared e to the negative t is linearly dependent, or excuse me, linearly independent on the interval I. And the interval I is negative infinity to infinity. Okay. Now let's do one where we know the answer is that they're linearly dependent, and then prove that the Wronskian is going to give us a 0. So let's say you've got that x squared and 5x squared, just to do a really simple example. The Wronskian of x squared and 5x squared comes from computing the determinant of this 2 by 2 matrix. The derivative of x squared is 2x, and the derivative of 5x squared is 5 times 2x, so that's 10x. Multiply across this diagonal and subtract. So we get 10x times x squared, which is 10x cubed, minus 2 times 5, which is 10. X times x squared is x cubed, and those reduce, and we just get 0 for all values of x. So that means that this set x squared and 5x squared is linearly dependent on the entire real line. Okay, now let's do another one. I think we had a 2x and an x squared and a 5x squared minus 4x. And we proved by definition that this was a linearly dependent set. Let's use the Wronskian to show that it's linearly dependent this time. So you've got 2x here, x squared here, and then 5x squared minus 4x. Those go in your first row. And then you compute the derivatives all the way down until it's a 3 by 3 matrix, and you're taking its determinant. The derivative of 2x is 2, derivative of 2 is 0. The derivative of x squared is 2x. The derivative of 2x is 2. The derivative of this guy is 10x minus 4, and the derivative of that guy is 10. Now you can expand along any row or column that you want, but when you evaluate this 3 by 3 determinant, it's helpful to use a row or a column that includes a 0 because it just makes your computation a little bit less. So I think what I'll do is I will expand along this column. And remember how this works. We have a sign convention. You always start positive here, and then you flip the sign as you go across the row. So you go plus, minus, plus, minus, plus, minus, pick up where you left off, plus, minus, plus. Now we ignore these signs over here, and we're just interested in these signs over here. Those are going to help us evaluate this 3 by 3 determinant. But before we do that, let's review how we evaluate these. You've probably seen this before if you've already taken Calculus 3. Whenever you evaluated cross products, you did something very similar. It was a determinant form of a cross product, and you had I hat, j hat, and k hat in the first row. So let's look at this here. Let's say you're finding the determinant of A, B, C, D, E, F, G, H, I. You can expand along any row or column that you want. I'll just use that first one. You've got to use that sign convention. Plus, minus, plus, pick up where you left off. Minus, plus, minus, plus, minus, plus. And then you can expand along any row or column you want. I'm just going to pick the first one, first row, for example. And this is how you break this down. You're basically taking this 3 by 3 determinant and you're turning it into a linear combination of 2 by 2 determinants. So we're going to take A, whatever that number is, and multiply it by +1. And then you want to cross out the row and column containing A, and then you see this 2 by 2 that's left. You want to evaluate that. And then we subtract B times this 2 by 2 determinant. And to get this 2 by 2 determinant, you cross out the row and column containing B. So you have a D and an and F, excuse me, a G and an I. And then we add, finally, C. And we cross out the row and column containing C. And we see this D, E, G, H. And we evaluate that. And remember, the 2 by 2s are just evaluated by multiplying across this diagonal and multiplying across that diagonal and subtracting. Now, if this was a 4 by 4, you could do exactly the same thing. You fill in your matrix, and then if you've got any rows or columns that have a lot of zeros, that's probably the row or column that you want to expand along. And then you would take your 4 by 4 matrix in that example, and you would split it into, or you would rewrite it as, excuse me, a linear combination of determinants of 3 by 3 matrices. And then those determinants of 3 by 3 matrices can be broken down to these determinants, this linear combination of determinants of 2 by 2 matrices and so on. So that's the idea. And that's exactly what we'll do here. Now I'm using this column because it has a 0 in it. And you can see why we want to expand along a row or a column that contains a 0, because I'm going to have 2x times a 2 by 2 determinant, minus 2 times a 2 by 2 determinant, plus 0 times a 2 by 2 determinant. And since I've got a 0 here on this last one, 0 times anything is 0. So it's gone, and it just reduces the amount of computation we have to do if we choose the row or column that has a 0 in it. So let's evaluate this now using this definition that we've listed here. Okay, so you're going to cross out the row and column containing that 2x, and I'll just write W equals. We'll have 2x times this 2 by 2 determinant. Cross out this row and this column, and you've got a 2x and 10x minus 4, and a 2 and a 10. And you want to ignore those red signs. Those were only for this column that you're expanding along. They do not affect the expressions in the 2 by 2 determinants that you're multiplying by here. So you've got 2x times that guy, minus 2 times this determinant. Cross out the row and column containing 2, and you have x squared and 5x squared minus 4x there in that top row. And then you've got the 2 and the 10 in the bottom row. And then you're adding 0 times this. Cross out, the row and column containing 0. And you've got that 2 by 2 determinant, but it doesn't really matter what it is because we're going to multiply it by 0 anyway. Now, remember, this set of functions is linearly dependent. We can look at it and tell if I take this guy and I multiply it by 5, and I take this guy and multiply it by -2, and I add them together, I get this guy. So this guy is redundant. This guy is not giving us any new information that we couldn't get from these other two. So we want to prove that using the Wronskian. And we can do that by evaluating this. Since the set is linearly dependent, we should get a 0. So we'll have 2x times this quantity. 2x times 10 is 20x, and then 2 times this quantity. If I distribute that, I'll have 20x minus 8, but I'm subtracting that. So if I distribute that negative, well, actually, I'll just write it like this. We'll distribute the negative in a moment. That's this times this, and you subtract that guy. All right, then here we've got a minus 2 times, multiply across this diagonal, and then you multiply across that diagonal and subtract. Now let's simplify. Let's move that, I'm saying factor. Distribute that negative through the parentheses, and let's distribute that negative 2 through those parentheses. So you've got 2x times 20x minus 20x plus 8 minus 2 times 10x squared minus 10x squared plus 8x. Those reduce, and over here you end up with 16x. And over here you have minus 16x. And so we get 0. So that tells us that the set of functions x squared, was it? No, not x squared, sorry. 2x and x squared and 5x squared minus 4x is linearly dependent on the entire real line. So if you get 0, the set is linearly dependent, which means that at least one of those functions in the set is unnecessary. One of them is redundant. One or more of them are redundant. If you get something that is non-zero here, that means that that set is linearly independent on the entire real line or the entire interval where those functions are, or where those functions are well defined. So that is how we compute the Wronskian. Let's just do one more. Let's compute the Wronskian of sine of x, cosine of x, and 1. So you've got sine of x here, cosine of x here, and 1. The question is this set linearly independent or is it linearly dependent? Well, in order to figure that out, I'll evaluate this 3 by 3 determinant. Take the first and second derivative of sine of x, so you get cosine of x and negative sine of x. The derivative of cosine of x is negative sine of x. Derivative of negative sine of x is negative cosine of x. Derivative of 1 is 0, and then the second derivative of 1 is, of course, 0 as well. I see that column of zeros, so I'm thinking, let's expand along that column. Use the sign convention, plus, minus, plus, pick up where you left off, minus, plus, minus, pick up where you left off, plus, minus, plus. And so we end up with 1 times the 2 by 2 that comes, or the determinant of the 2 by 2 that comes from crossing out this row and this column. You've got cosine and negative cosine on that diagonal. And you've got negative sine of x and negative sine of x on that diagonal. And then you're subtracting 0 times something, and then you're adding 0 times something. And of course, that means this whole piece is 0 and this whole piece is 0. And so we've got cosine times cosine, or cosine times negative cosine is negative cosine squared. And then we're subtracting sine of x times, or negative sine of x times negative sine of x. Negative times negative is positive, so it's positive sine squared x, but you're still subtracting it. And if you want, you can factor out that negative 1, and you see the sine squared plus cosine squared x there, which is 1. So if this is 1, the Wronskian is negative 1, and that's not equal to 0. So that set of functions, sine of x, cosine of x, and 1 is a linearly independent set of functions. So if we were looking at a third order differential equation and all three of these happen to be solutions to that equation, the general solution would be c1 times sine of x plus c2 times cosine of x plus c3 times 1. And that would work. That would be our general solution because all of these functions, all three of these, contribute something unique to that general solution, which is exactly what we're going for.